We'll just get started now. Thanks for joining us today and welcome to our virtual lunch and learn for August. My name is Mark Foer. I'm a client engagement principal at DS and also the machine learning practice lead. Presenting today will be Nigel Hook, our machine learning tech lead, and Nabi Rizvani, one of our lead data engineers. Before we begin, I'd like to acknowledge the traditional custodians of the lands that we are meeting today. I pay my respects to the elders past, present and emerging, and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Australia. I also acknowledge and pay my respects to our Aboriginal and Torres Strait Islander people and colleagues joining us today. Now for some quick housekeeping, we'll be answering questions at the end of the presentation using Slido, so please feel free to type them in as we're going so you don't forget, and I believe you'll be adding that to the link. If you would like to turn on captions, you can do so by clicking on the three dots at the bottom of the screen, as you can see in that screenshot there, and selecting captions. And as usual, this session will be recorded and made available to you for future viewing, or if you'd like to share with your colleagues. Now, for a quick introduction to DS for the folks who haven't worked with us before, we're an Australian technology consulting company made up of about 150 people, primarily across Melbourne and Sydney, though I should say with COVID, we're scattered across various parts of Australia now. We've been around for about 17 years now, love building end-to-end solutions for and alongside our clients. We've got our own products, so the approaches we take and love to share are often based on what we've learned on our own product journeys. The best way to describe us is that we figure out how to best use emerging technology to help our clients solve their biggest problems. And we do this by bringing together elements of digital data and devices, taking a cross-functional approach and putting experience design at the heart of it all. Today's talk is the latest in our machine learning series. For those who have been following us, you would have heard us speak about machine learning application areas such as computer vision, how it's being used in the field, how to get your models to production, and other related topics. Today's talk is around data readiness, for machine learning. Earlier in the year, we asked organisations across Australia to complete a survey about how they're adopting machine learning. Over 200 organisations responded, and we released those findings in our report, and also shared those findings in a lunch and learn similar to today's session. If you haven't downloaded the report or haven't watched the video and would like to do so, again, we'll share the links at the end of the presentation. The report showed us that data-related issues were either the top or the second most commonly reported challenges when organisations have begun their machine learning journey. And that's certainly consistent with what we've seen when working with our own clients, and is the key reason why we're sharing our insights today. And at this point, I'll pass over to Nigel, our junior tech lead, to kick off the main presentation.
Thank you, Mark. Hello, everyone. My name is Nigel Hook. I am the machine learning lead at DS, as Mark mentioned. So I want to start this talk with mentioning experience we had with a client. So we're working with an agency rating service that was collecting customer feedback comments on behalf of its clients. And they asked us if we could use sentiment analysis, a kind of machine learning, to classify these comments as either positive or negative in sentiment. And close inspection revealed that the vast majority of the comments that they had in their database were positive. And the implication for machine learning was the scarcity of negative comments meant that it was difficult to train a model that worked effectively. And essentially, we weren't able to beat the most simplistic possible approach, which would be just to always predict that a comment was going to be positive, because that would be correct more than 99.9% of the time. So this was a problem, but experiences like this are not uncommon. And I'll come back to this one later, but this talk really is about how you can do better than this and avoid situations like this. So what we're going to talk our way through today is give you some background to how we see this whole data readiness situation in the context of a data journey. We'll talk about what the role is that data infrastructure plays in that, some ways to assess your own data readiness, and talk through some real-world examples that we've worked with and some tips on how to get started. So data presents a variety of problems for machine learning, and the most common challenges reported in the machine learning survey that Mark introduced this talk with, and that we've also observed commercially, really are these. So lack of data strategy resulting in lack of coordination, or of not being able to access data because of organizational challenges, regulatory or privacy concerns, getting access to consistent and appropriate quality data, inadequate data infrastructure, and then issues around data sets associated with training and testing of machine learning models. So, as I mentioned, we see this situation as a data journey. And what happens is, as data grows in importance, each business has to lift its capability to acquire and use data. And you can think of this as a journey which will transform the organization. And ultimately, this transformation is going to affect all aspects of the business. One way to be guided through this transformation is by considering an analogy with Maslow's hierarchy of needs. Psychologists recognize that people need food and shelter before they're concerned with friendship and self-actualization. And similarly, there's a hierarchy of needs with data. So looking at this pyramid, which is a way of depicting this hierarchy, if we look at the bottom and work our way up, first of all, organizations have to collect data as the first step using sensor measuring devices or online forms or access to financial transactions, etc. And once you have the data, you have to store it somewhere. And then you can analyze and understand the data and summarize and present it to share insights. And so you see we're working our way up, but all of this helps to develop data literacy as well in the organization. And once you've quantified the insights, you can optimize the business operations, and you can then effectively build and apply machine learning models for prediction. So you can think of this as I said, a hierarchy of needs, and you can also use this to assess what do you need to do to reach a certain business outcome. So if your goal is to do analytics and reporting, so that's roughly in the middle of the pyramid, you have to pay attention to what lies below that to some extent. Now, we're not advocating that you need to build the perfect bottom layer of the pyramid before you consider the one above it at all. What we're saying is these layers are foundational, and to some extent, you need something at each layer below where your goal is. But the best way to make progress to a goal is to make it in a thin vertical slice where you have just enough implementation or attention to each layer below it, sufficient to achieve the outcome that you want. And we're going to use this diagram as a guide to navigating the data journey. And please notice this is not a perfect analogy for what you have to go through as an organization. It doesn't show data governance or ethical concerns, but there needs to be parallel growth in attention to these too. So let's first consider the data itself, and I'm going to hand over to my colleague Nabi now to take over from here. Thank you, Nabi.
Thanks, Nigel. Good afternoon, everyone. My name is Nabi. I'm a lead data engineer at DS. Just a second while I pull up the slides. Okay, so today I'll be talking about the data journey towards ML and what it means in terms of data. Okay, so going back to this analogy of hierarchy of needs and how we wanted to apply that to communicate what we mean by a data journey for adopting machine learning. So let's start with the bottom level of the hierarchy, which is the most foundational requirements for basically adopting data and machine learning. Okay, so you may ask yourself, why do I need a data infrastructure? Can I not use a database? And to answer that question, so basically, handling and processing data can be quite complex at times. And I think these 3 V's kind of cover different aspects of those complexities quite well. Okay, so let's start with volume. So you may work with different data sets in different sizes. So you may start with smaller data sets that are just a few megabytes. Then you may come across larger data sets that are in like gigabytes, and even you may have experienced much larger data sets that are in petabytes. Also, variety of data can make it a bit challenging as well. So you can basically have different data sets in different formats. So you can have tabular formats, structured data, you can have semi-structured data in JSON and XML or other formats, or you can have completely unstructured data in form of images, videos, and text. Also, the velocity of data is very important and can impact the complexity of it. So you may basically have data that you receive in batches, or you may have streams of data that flow into your ecosystem and you need to deal with. Okay, so let's have a look at the data infrastructure that you need. So you might have heard this terminology of a data lake, and that is commonly the kind of data structure that you need to be able to basically do big data analysis and machine learning. So what a data lake is, it's really a relatively cheap and scalable storage mechanism for the most part. So at the center of this visualization, you see that storage mechanism and the data from different sources, it can be databases, files, or data streams, flow into this data storage means. And then you can have different zones in your data storage, in your data lake. So you can have raw zone, you can have process zone, and then you may want to have a dedicated zone for your results. And then basically you can build the pipelines. So pipelines are basically the tools that do the lift and shift from your data lake and then provide the data to processing engines and then bring it back. So you can use general purpose big data processing engines like Spark, or you may use more specialized machine learning processing tools. And then once you have the data, you may make it discoverable to your end consumers, and then you may provide it to them in different formats through your interfaces. Okay, so to just provide an example of a data lake implementation on cloud, just wanted to show this example from AWS. So this is obviously just an example. So different cloud providers and cloud vendors have implementations of data lakes. Google Cloud and Azure have their own implementations, but this is just an example from AWS that you might be more familiar with. So you have this AWS lake formation, and at the center of it is the Amazon S3, which is the distributed file system, basically service of AWS, which you use for storing your data. And then there are two key components in this AWS lake formation, basically the ETL pipelines and also data catalogs that work very closely with the storage mechanism. And also you can have different processing engines, so SQL-based processing engines like Amazon Athena and Amazon Redshift, and also scalable in-memory processing engines like Amazon EMR, which is an implementation of Spark. And then you have Amazon SageMaker, which is the specialized ML service within AWS. It's also worth noting that so different cloud vendors provide reference architectures that you can look at and follow, which will give you ideas for implementing your basically data platform and data ecosystem. Okay, so once you have built a data infrastructure and a data lake, the next step will probably be to look at building some analytics and reports. So analytics are basically the first step towards extracting insight from data. They're normally used to communicate business metrics with different stakeholders, and they might be used to measure those business metrics as well. And they can be quite helpful in basically making business decisions based on data. What's really important here is that not only analytics can be helpful in driving some basically business decisions, they can also be helpful in basically highlighting data quality issues early on in your data journey as well. Okay, so we talked about the infrastructure that you need. We talked about how analytics can be important in your transition from basically just an infrastructure towards adopting ML. So obviously analytics are not always enough, so you need to be able to predict. Analytics are more backward looking, and you need to be able to forecast and personalize, and you need a way of basically forward looking as well, and that is why you need ML. Okay, so when you want to start with machine learning, probably the first question that you might ask yourself is, what problem should I start with? So normally with any initiative that you want to start with, especially those that you don't have much experience with, you want to start with the least complex problems. In the context of machine learning, you want to do the same. So if you look at this chart, it's actually looking at two different dimensions if you want to categorize machine learning problems. So if you look at basically complexity and business benefit as the two dimensions, you want to basically be focusing on the machine learning problems that are the least complex and at the same time can bring you the highest business benefits. And that is important in the context of data as well. So the least complex problem that you pick to start with, basically the least complex data challenges you will come across as well. Just to provide an example, if you want to work on a machine learning model that needs data from different sources and different data types, for example, you want to work on a machine learning model that needs text and images. So definitely sourcing that data will be more complex. Building a model that can work with multimodal kind of data will be more complex as well. So you might want to focus on probably just text to start with. Okay, so how do you normally approach machine learning problems? You normally start with a POC or a proof of concept. And what proof of concept is basically, as the name suggests, you really want to focus on the business value that you can get out of the machine learning that you're building. You want to test out the feasibility and the business goal that you are aiming for. And then, yeah, you just want to do a low-cost proof of concept to basically test out your hypothesis. So the key message here is that, as Nigel mentioned before as well, so you want to build a thin vertical slice when it comes to investing in your infrastructure and basically investing in analytics as well. So you want to start small. So you just want to invest in building as much infrastructure as needed. And once you're done with your POC, you can iterate and basically improve the underlying infrastructure. Okay, so after doing the POC, and by assuming that you've successfully finished the POC, you move on to productionizing your machine learning model. So it turns out the efforts required for productionizing a machine learning pipeline and delivering a production-ready machine learning model are just not limited to the ML code and ML algorithm itself. So there are a lot of other activities and efforts involved in the process of basically productionizing machine learning pipeline. So we may think about data preparation aspect, which is basically you want to make sure you have a more strict data collection and data verification process in place. And also you want to make sure that the underlying infrastructure for serving your results is quite resilient as well. Now, productionizing in itself can be a very broad topic, but just to mention a few examples of the activities that are involved in productionizing the machine learning pipeline. So to serving infrastructure. So before I talk about that, so basically the term ML ops that you might have heard of before is basically intersection of skill sets from machine learning, DevOps, and data engineering. And that's a relatively new term, but it's growing in popularity. Okay, so going back to ML ops consideration for productionizing a machine learning model. So you want to think about the serving infrastructure. So obviously you want to have a serving infrastructure which is scalable. And then depending on the type of data that you want to basically test and use this machine learning model with, if you're basically using it with batch data versus streaming data, you need to have different considerations. Also, you need to be sure that basically you are versioning your model and data, and that is very, very important. So you need to automate that process somehow so that you know what version of input data was input to what specific version of your model, and then what version of results it actually generated. So that way you'll be able to more efficiently basically evolve your model and keep track of its changes. One last thing, which is also very important. So monitoring models' performance over time is also very, very important when you are basically delivering a model to production. So since the data changes over time, so the performance of your model may degrade over time, and that's because the data that you're testing with is not necessarily the same as the data that you initially trained your model with. So you need to monitor that, and in case the model degrades, you may consider retraining your model. Okay, so we talked about the hierarchy of needs and use that analogy to basically discuss different considerations and different basically aspects that we need to think about when it comes to adopting ML. There are other considerations that basically are not covered in that hierarchy of needs, and we'll briefly touch on those as well. So data strategy is basically a very important thing to have in mind if you want to basically be successful in your ML adoption journey. So what data strategy is really a roadmap that helps you basically transform from a conventional organization towards a data-driven organization with data-driven culture. And that is basically a roadmap and a detailed plan that helps you get there. So what does a data strategy entail? It is normally basically concerned with people, processes, and technology. So although data strategy can be very different for different organizations, can be like very elaborate, or it can be very brief. Here, there is an example of a data strategy, and it's good to just have a look at it to get an idea of what we mean by data strategy. So you normally start with business requirements, and that is basically the first step of your data strategy. And then based on that, you start sourcing and gathering data. You think about the technology infrastructure and basically starting to extract some insight from your data, what we already discussed. And then people and processes. This is a very important step in your data strategy. So you need to basically have a unified organizational structure to be able to basically make decisions towards basically successful adoption of machine learning. For example, if your data is not ready for machine learning, if you don't have an organization which is not making decisions holistically, you may hear things like, okay, fixing or addressing data issues for ML is not a priority, and that's what you want to avoid. Also, you need to think about data governance, and this is a very broad topic, but just briefly to give you an idea of what it means. So you need to make sure that the data is discoverable, and also you need to make sure that the right people have access to the right data. Also, you need to be able to define the data lineage, where the data is coming from. Okay, so once you have all these steps in place, you basically can prepare a roadmap, set yourself goals, and work towards achieving those goals. One last thing that I wanted to mention here is data privacy. So you keep hearing about data privacy and how important it is to basically avoid violating data privacy regulations and like keep people's data privacy. So we wanted to touch on that here as well. So in the context of data privacy, what you really need to think about is two main things. So you may ask yourself, basically, if I'm gathering some sort of data and if I'm storing it somewhere, the first question you want to ask yourself is, if it contains sensitive data, do I really need to store that data? And if you do need to store those sensitive information, you need to be able to protect it somehow. And that is done through normally anonymizing and encrypting data. So now, although it might sound very trivial to basically comply with data privacy guidelines, we keep hearing in the news every day that even huge organizations and huge corporates are basically incurring huge fines because of violating data privacy regulations. So it damages their reputation, obviously, and it may impact users' privacy because of basically private data breach as well. So this is something that we need to think about and can be very critical in our data adoption journey. Okay, with that, I'm going to hand over to Nigel, and he will talk about data quality in more specifics of data quality. Thanks, Nigel.
Thank you, Nabi. Hello again. So, as Nabi said, we're now going to talk about what the role is of data quality in supporting data readiness for ML. Now, for machine learning, having the right data is as important as having the right algorithm. And typically, organizations think of data quality as in terms of concepts like accuracy, completeness, consistency, whether it's up to date, etc. And this definition makes sense when the data is intended for traditional business functions like order processing, business analytics for decision making, or record keeping for financial or compliance reasons. However, machine learning uses data differently. And in particular, machine learning pays very close attention to the statistical properties of the data. That is the way it's distributed in the technical sense of statistics. And frequently, machine learning models will be drawing on data combined from different sources, which possibly haven't been combined before in that organization. And ultimately, with ML, we're trying to predict patterns in data we haven't yet seen. So this is quite different from the way that businesses typically use data, and we have to think about quality a little bit differently as a consequence. And here I want to give credit to Neil Lawrence, a British computer scientist at Cambridge University, who proposed this model of data readiness levels that I think has a lot of merit. So I'm presenting it to you today in summary. So what we're proposing here is a measure of data readiness for a specific purpose. So that is, we're looking at the data, but we're also thinking about what we want to use it for. And it's putting those two together that is the key difference from a more traditional approach to data quality. Now, Lawrence proposes 3 broad levels of data readiness. And you can see I've shown them in this diagram on the right. Each of these levels, firstly, each one has quite objective quality characteristics that you can use to assess the appropriateness of that quality level for data for a particular purpose. And secondly, each of these levels really requires a different set of skills, increasingly sophisticated skills as you go up the stack in order to assess readiness at each level. So starting at the bottom then, we have level C, accessibility, and this really is addressing these questions. Does the data exist? How do I access it? And can I ethically use it? So below this level, you really have what we call hearsay data. That is data that is rumored to exist, or someone believes that the organization might have collected that data. We have it somewhere. You might have to go looking to find it. But you don't know for certain that it exists. So once you've sorted out these basic questions around the data and you've qualified the data to this level, essentially what that means is you can read the data into a software application for analysis. So that's the lowest level of readiness. The next level up is level B, fidelity. And this addresses questions like, how was the data collected? Was it aggregated in the form that I see it? Is that exactly how it was measured, or did someone combine the data in some way? Because that's going to change how useful it is for machine learning. And how accurate is it? In other words, is it a true representation of reality? Now, data is always only an incomplete representation of reality, but for a particular purpose, is this sufficiently accurate for my needs? Now, assessing a data set to this level is quite a lot of effort, and this is typically where exploratory data analysis happens. And qualification of a data set to this level really means that you understand the limitations of the data. When we get to the top level, this is level A, we're now thinking about the context of the data, and we're specifically tying it to the purpose we have in mind. And the question is this going to be suitable for my purpose? To answer this question requires a thorough understanding of the data set provenance. That is, everything that has happened to this data from the moment it was collected and the way it was collected right up to the point of where we're at now. And a key detail here is that a data set which is qualified at this level, level A, for one particular purpose, may be only level B for another purpose. That is, the fidelity is obviously the same in both cases, but it may be suitable for one purpose, but not for another purpose. And traditional data quality efforts tend to ignore this level of the analysis. So let's talk about an example here. A data set may have been collected in a way that resulted in significant bias. For example, consumer behavior data that was collected during pre-pandemic times might reflect a particular set of consumer priorities, people's purchasing behavior, for example. By traditional data quality measures, this may be high quality data, but it may be totally unsuited for training a model, an ML model that is needed to make predictions in the current situation, where I think most people would agree that consumers' purchasing behavior is likely to be different. So now we're going to look at some real-world examples of this that we have encountered at DS, and these are going to cover a range of situations and highlight these issues. I'm going to start with the example I introduced the talk with, which was the customer feedback sentiment analysis problem we looked at, where the customer had an unbalanced training set with far more positive sentiment comments than the number of negative sentiment comments. And as we investigated this with the client, what we discovered was the business process they were using for soliciting and collecting the feedback was ultimately flawed. So they were collecting accurate information, but for this purpose, they were very biased in the way they were collecting the data. So we ended up with a level A issue. So I've got that diagram there in the top right corner of the screen. You can see which level we're talking about. So this is a data suitability issue. And really, the only way to solve this problem was for them to change their business process for soliciting comments and collect fresh comments that were more balanced. So another example was a question posed to us by a music streaming service. So this was a company whose business is all about streaming music into commercial venues to provide background music for patrons at those venues. And the question was, does the music that people are listening to affect their purchasing patterns? Now, they had collected two data sets, one for a period of time. One was the playlists that were played to the patrons, and the other was details of all the cash register transactions as customers were purchasing products at these venues. And neither of these data sets had previously been analysed. When we looked more closely at the data, the first thing we noticed was that some of the data was missing. And more importantly, the number of patrons present in the venue at any time wasn't measured. And ultimately, this meant that we couldn't really calibrate the scale of the transactions when one particular song was being played to make it comparable with the transactions when another song was being played. So ultimately, this was a level C issue, missing data. And at this point, we worked with the business to talk about ways they could measure patronage. We talked about using CCTV footage to count heads in the room, etc. And that was really the way forward from there. Another example was working with a major beverage company that wanted some help identifying performance issues with an automated bottling machine on the production line. So this was a complex computer-controlled machine that had quite a lot of internal state in it, and this state could be extracted over the data network, and it was being pulled out and stored in a data warehouse. And so what we were hoping to do was just go in and look at the data, and particularly the state of the machine at the points where the bottles became jammed or fell over or some other fault happened with the machine. Now, as we look closely at the data, what we found, though, was that we couldn't make sense of it. And looking more deeply, we found that the individual state variables that describe exactly what a machine is doing at any moment in time were being polled from the machine at a rate that was slower than the bottling rate. So essentially, we weren't getting a coherent picture of all of the state variables as each individual bottle was being processed by the machine. And so this is an example of a level B issue that put together, we weren't getting a coherent picture of reality. So this is a fidelity problem. Additionally, talking to the business, we found that they were not accurately measuring the machine output either. So even if we had solved this problem, we would have struggled to have a data which represented a baseline for comparison in terms of improving the performance of the machine. So we worked with the business to establish new performance measurements and changes to the way the data was sampled from the machine so that this analysis could go ahead. Next example is a one where we were working with a financial institution to match customer details against mandated surveillance watch lists. And this involved record matching. And in particular, we had to gather what was known about the customer and their transacting activity across a number of different parts of the financial institution. And what we found, though, was that each part of the organization kept only the information about the customer that was relevant to their needs. And what that meant was when we tried to merge this together, some of the details could not be precisely aligned. So again, this was a situation of data suitability. Possibly there's an elements of level B as well in here, but primarily a level A issue of data suitability. What we did realize too, though, is that this wasn't a serious problem. There were inaccuracies, but they were considered minor, and the model predictions were going to be used in a way where they were going to be reviewed by a human anyway. So this wasn't a showstopper, and we were able to proceed with the project. Next example was a case where we were helping a client develop a machine learning powered mobile app to recognize items in photographs, so using computer vision object detection. And the customer had attempted to do this themselves. They had collected some training data, trained a model, and their initial attempt didn't give results that they were satisfied with. So that's when we got involved. And what we discovered was the reason that their trained machine learning model, the reason it wasn't working well was because the training images they were using were taken with a particular camera and lighting situation that resulted in images in a different format from the way they would be taken with the mobile phone camera. And the lighting conditions were typically different from what would be seen by the user, the end user, using their camera to take the photographs. And furthermore, there just weren't enough training images anyway. So this really is a level A issue of data suitability. And what we were able to do, though, was work with them to get around this. So the first thing we did was change the machine learning model to a different one that was less sensitive to the image format and also the lighting effects. We synthesized additional training images from the ones that they provided through data augmentation, and consequently we're able to build a machine learning model that worked for their needs. And the final example I'm going to mention to you relates to a teleradiology provider, which is a medical consulting service that receives medical diagnostic scans from different hospitals and clinics and receives them electronically, and it queues them up, and then radiologists review each scan and write a report and send it back to the clinic. And as these scans are queued up waiting to be processed, what this company wanted to do was reorder the scans so that they could prioritize those which were brain scans, because typically the situation when a brain scan is done is often it's a matter of life and death, and minutes matter in terms of getting the report back to the clinic as quickly as possible. So the idea was that we would have an image analysis machine learning model which would look at the scan and decide whether it was concerned with a brain or not. And that would be used to prioritize the images, the scans for analysis. The problem for developing a machine learning model was, however, that there were no pre-labeled images. So the belief was that you needed to have a radiologist mark up a set of training images, and each one would have to be labeled as either brain or not brain, and that's how we would train our binary classifier. The problem there was that the radiologist's time was considered quite expensive to the business, and they didn't want to dedicate that time just to this task. We were able to work with them to get around this problem, however, because they had an archive of a large number of these scans together with the text of the reports that had been written associated with the scans. And we were able to train a natural language processing model to go through the text of the reports and classify them as brain or not brain, and then use that classification to tag the images as brain or not brain. And from that, we could build a machine learning model to classify the images. So we're now coming towards the end of our talk. And if you think about where we've come along the way, we introduced the concept of this data journey and the idea of the data science hierarchy of needs and the use of that to guide you on the journey. We talked about the infrastructure that is implied in this hierarchy and necessary to achieve successful outcomes at the higher levels of the hierarchy, the need for a data strategy, and we introduced you to the data readiness scheme proposed by Lawrence, where you assess a data set's suitability for machine learning, in not only in terms of the quality of the data itself, but also looking at how suitable and appropriate it is for the context that you're intending. And finally, I just want to leave you with some thoughts on how you might get started on the journey if this is the situation you find yourself in now. So DS advocates taking an agile approach where you think about your infrastructure development in terms of small experiments. The first step then is to assess where are you on the journey. So think about the hierarchy of needs, try to put yourself somewhere on that diagram, assessing your maturity, and then look at the current state of the data that you're using now, which is giving you business value. Consider its quality attributes, how well it is serving you. Try to measure any errors that you're finding in the way you're collecting and processing that data, fix them at the source. And once you're satisfied that you're getting best value out of the way you're using data right now, then think about moving forward, think about selecting the right problem, identify the necessary data, assess your readiness as you get that data ready, and only then build the necessary infrastructure to do that, to take you to where you want to go, but don't build any more than what is necessary. And finally, look around at similar organizations who may be publishing about what kind of data architectures and approaches they're taking. Look at the reference architectures that are proposed by the various cloud vendors and get ideas from them that might be relevant to your situation. Thank you very much. Let's take it from there, take some questions from there. And Mark, I'll pass back over to you now.
Thanks, Nigel and Navi. I'll just jump onto Slido now. And the first question we have is from Derek, actually. G'day, Derek. Can an AWS data lake act as an aggregator of multiple application data sources, i.e. non-AWS hosted ones? Or do I need another aggregator? The example there is a tool like Segment. Might one for you, Navi?
Yeah, so I think it's an interesting question. So one important thing to have in mind is that moving data between different cloud platforms is costly, and we should be clever about like what specific data sets we actually need to move across. So that's the first consideration for me. And also, the data lake in itself is meant to be the facilitator. It's supposed to be basically the area where you have flexibility to do whatever you want. It's not necessarily where you have to bring in all your data. So you should think about it as an area where I can actually bring in the data for different analytics and machine learning purposes. It's not like I have to bring everything. Also, these days, we're hearing ideas of like data mesh, for example. And that is basically distributing storage and management of data. It doesn't have to be a centralized mechanism like a data lake that stores everything. So it can be spread across organization, not necessarily even in one cloud platform. And then based on how you architect your solutions, you can basically have your data distributed across your organization as well. And then the last thing that I wanted to mention here is, so there are cloud agnostic data solutions like Snowflake and Databricks. So they actually offer services in pretty much all the cloud vendors. And then they offer you this capability of like moving your data between cloud platforms without incurring much cost. And that is something that can be considered as well.
Thanks, Navi. Next question here, and I think this one's directed at you, Nigel. You've given examples where people collected data in the wrong way. What is the right way to collect data?
Okay, thank you, Mike. So I would say that the first thing is think about the end goal that you're aiming for. And there is no simple answer to this question, but there are some common mistakes. So I mentioned things like not sampling. So something that is changing rapidly, you need to decide how frequently you're going to sample that if you're trying to create a coherent picture of what is going on. Obviously, you need to measure it with sufficient accuracy. So if it's a physical quantity, how many significant digits of accuracy are in the numbers that you're basically getting into your digital form of the data. You need to consider whether you're likely to miss any data, and does that actually matter for the purpose that you have? Is the data that you're collecting going to build a sufficiently broad picture of the real situation that, for example, if it's a machine learning model, do you really expect that the model is going to have enough clues in the data you're collecting to be able to make the predictions that you want from it? So these all require a little bit of expertise to answer, I think, and it's going to be a different answer for every situation. But ultimately, they're all directly linking the way you go about collecting your data to the ultimate purpose that you have in mind for using it. Happy to talk to anyone further about a specific situation if they need more particular guidance about that.
Okay, perhaps this is the last one, given the time that we have left. Is there any way of fast tracking whether we have a data readiness issue?
Yes, that's a tricky question. Look, I think you can do a quick survey to get some degree of confidence there. One question I always ask in an organisation is, does anyone actually look at this data? Am I the first person that's likely to have ever looked at it? If it's someone's job to look at this data, or if it gets used to produce a monthly report or something like that, then the chances are that the data's not too bad, at least for that purpose. It's likely to exist and not have too many holes in it. When it comes to data that's being used to train a machine learning model, there can certainly be subtleties there that don't show up until you do detailed analysis. And so I'm not aware of any way to fast track answering those ones. They are the hard cases, I think, and you've got to be thorough with your analysis, really.
Great, thanks everyone. Just wanted to say thanks for everyone for joining us today, and thanks for those who have asked those questions. If there are any other further questions, or if you'd like to deep dive into any of the content that we've covered today, we'd love to hear from you. As I mentioned at the start of the presentation, we'll be recording this, or we have recorded this, and I believe it'll be made available later this afternoon or tomorrow at latest. We will share that with you and also provide our contact details. Thanks again, and enjoy the rest of your afternoon.
Thanks, Diaz.
Thanks, everyone.
Thanks, everyone.